Hello, guys, and welcome to another of our deep clustering series. And in this episode, we'll be talking about the improved deep embedding clustering. In a previous episode, we talked about the regular deep embedding clustering, and I highly recommend watching this video before watching this one. And this comes from this paper here, which was released in 2017, and we implemented it in this notebook, the same that we implemented the regular deck. So we'll be also using the Minis dataset. And for those who don't know Minis dataset, how does it work? It basically, these are 70,000 samples of handwritten digits, and these digits are represented in a 28 by 28 grid of these elements here. So each sample represents a single vector of 28 times 28, 784 elements that in the end you can see visually represent a digit. So these are our predictors. Okay, so let's see how IDEC works. It works the same way as DEC works. So basically, it uses the autoencoder to encode these 784 element vectors into a smaller, reduced, but representational uh, version of it. So yeah, basically the first part is the same as DEC. We pre-train the autoencoder to be able to compress our data. But the difference here is that we'll be also using the decoder in the fine-tune process. And what I say about the fine-tune process is the clustering part, as it is to say. So yeah, the pre-train part is where we train our autoencoder, and the fine-tune is the train loop of our DEC part, of where we also fine-tune the autoencoder in this part. The same way we did for DEC, we'll be doing here. We'll be fine-tuning our encoder, but we'll be also fine-tuning the decoder. And how does the loss function works here? Well, as you can see here, there's this equation where we can see the loss equals the reconstruction loss plus the clustering loss times a gamma factor here. So, well, DEC, regular DEC, only uses the clustering loss. In this one, we'll be using also the reconstruction loss. And well, we're not using the 100% of the clustering loss as we usually do in DEC. In here, particularly, we'll be using a gamma factor that we'll be talking about later. But this is basically our loss function. And what exactly is a reconstruction loss? As you can see here down below, this is our reconstruction loss. It's basically this Zi is our latent space. So it's the reduced space of the reduced vector of our sample of our digit. So it is the encoded sample. So we're basically decoding it again to see if it matches uh, our 784 vector in the first place. So we're gonna see if encoding and decoding how much does it change in reality. There's gonna be a little loss in this process because our autoencoder is not perfect. But the important thing is that this fine-tuning process that usually DEC does for the encoder can could distort the embedded space, reducing the clustering performance. So this is the idea here. We'll be also adding in our loss function the reconstruction loss during the training loop, during the train process. Okay. So yeah, basically we'll be using the same functions as we did for DEC. We're going to compute the initial centroids using k-means, returning the cluster centers. We're going to also use this specific function for computing the clustering accuracy, because this is not a simple accuracy process for what is usually computed. And this is our IDEC class. We also included the decoder uh, in this IDEC class, and it's going to be fine-tuned. These are centroids, which are also trainable parameters. This is our soft assignments, the same as DAC. So if you want to know more about how the soft assignments and the target distribution of DAC works, I highly recommend watching the previous DAC video we did about. And well, let's get to it. For the hyperparameters, we used the same learning rate as DAC, this number here. And we're also using the gamma here. That's the new hyperparameter that doesn't exist for DAC. And we're using the same other hyperparameters as we did for DAC, same number of epochs, same update target here. Number of classes are 10. There are 10 digits, so therefore there are 10 classes. And here is where we initialized our model, our initial centroids, our optimizer, and our scheduler. There's just a small difference here from DAC. The gamma decay factor here for our scheduler is going to be 0.9, so a very slow decay in a step size of 100 epochs. So it's going to decay our learning rate for 0.9 factor here every 100 epochs. So this is our train loop here. This X represents our samples, which are flattened to a single vector of 784 elements. We set our model to the train mode. We zero our gradients, our weights. We return our latent representational embedding here, which is Z. And no, basically, yes, this is our latent representation, and Q represents the soft assignments. Sorry about that. And in here, something very important to notice, to avoid instability, P, our target variable, will not be updated every epoch. So this is very important to add in the train loop. So we'll be basically updating our our target variable here every update target every 15 epochs. So this is very important to avoid instability in the train process. This is the same as we calculated for DAC. So this is basically the Kullback-Leibler loss. This is our clustering loss, therefore, and in here we'll also use the reconstruction loss. So as you can see, Z is our latent space sample, which are basically 10 elements, a reduced vector. So we'll be decoding this again, and we'll be using the mean squared error loss between the decoded sample and the sample. Okay, and this is going to be our reconstruction loss, which will be very tiny. You can see here the reconstruction loss is going to be very tiny, 0.013 and so on, but it's going to get inside our loss function. Okay, gamma here is a very low digit, so it's only 10% of the clustering loss, because gamma is, as you can see here, 0.1. So it's going to be gamma times the clustering loss. The clustering loss is a bit higher. So as you can see, is 0.15 in the first epoch. So yeah, by reducing this to a tenth of it, is going to be very close to the reconstruction loss, and well, therefore the reconstruction loss and the clustering loss will be very close to each other. So yeah, it's going to be 0.01 plus 0.015. This for every following epoch here. So yeah, basically our loss function is what we saw earlier on, and well, this finishes our train loop here. As you can see, and in here we calculate our accuracy score, and as you can see here, there's a big jump in our accuracy score, is basically 84%, which is a very reasonable number. And in comparison to DAC, Well, as you can see here, regular deck had only 75% of accuracy. So improved deck really showed himself a very useful tool. Just a minor adjustment in the loss function, and also adding up the decoder in the train loop really improved our model, and it proved to be useful in the end. So I highly recommend, if you're ever implementing deck, just taking this into consideration and implement IDEC. So I want to thank you for watching this video until now, and well, I hope you enjoyed this video. Goodbye.